Hello everyone, welcome back to our latest lecture session. So in the previous session we looked at the relevant theoretical basis for looking at calculating the equivalence point, right, when you are titrating a weak base with a strong acid. And we knew that the pH of the equivalence point would depend upon the pKb of your particular weak acid, and also to a little extent, not to a great extent though, on your total base present in your system. So in today's session we are going to primarily look at applications of VMINTEQ, and then if given the time or time constraints, looking at the time constraints, we are going to move on to buffering, I guess. So let's switch over to VMINTEQ here. So now we are going to look at how to look at the applications of titrations in our particular system here. So we look at two examples, one when we have the H2SCO3 present in our system. So let's choose the relevant components for that. So I'm going to say CO3 total, and that let's go with again the same case as last time, let's say 0.001, right, okay, or 0.01 for now, 0.01, and I am going to add that to the list. And then the other component obviously is going to be H plus, and if CO3 2 minus is 0.01, our H plus needs to be, or H total needs to be 0.02, right. So I am going to add that to the list. And obviously why is that? Because H2CO3 is our initial what do we say, our source or recipe, right. So let's just look at why, I guess, right. So I am saying that I am adding H2CO3 to the system, right. So and if I am choosing H total and CO3 total, what is the component balance going to be equal to? It is going to be equal to 2 times H2CO3 concentration added initially, and CO3 total is going to be equal to 1 times the H2CO3 added initially, right. And again obviously if I am choosing NaHCO3, right, as my recipe species or the concentration or the compounds that I am adding initially, what would H total be then? It is now going to be equal to 1 times NaHCO3 naught, right, and CO3 total, that is going to be equal to 1 times NaHCO3 naught. Again for this particular VMINTEQ example, I am looking at this particular scenario, right, when H2CO3 concentration is equal to 0.01 molar, right. So again let us go back to VMINTEQ here and let us look at the view edit list. So obviously CO3 2 minus is 0.01 molar, so there will be a minor error because these are molar units and not molar, and H plus is 0.02. So back to main menu, obviously it is a closed system, so no gas is present in that particular case. And now we have a particular tab here that says multi-problem or sweep. So and when you come to this particular page, you see that you have sweep, titration, simulate evaporation or concentration, or multi-problem generator. So the two aspects we are going to look at for now or for this session are going to be titration and sweep. So let us look at titration, right. So let us go to the titration manager. So it is going to ask you for the arbitrary units of the volume that you are titrating. So arbitrary units, right. So let us, I will just for the sake of ease I am going to choose 100, let us say, right, and the volume of the titrant, let us say I am going to choose volume of titrant is going to be per step. So I am going to choose it is 1, right. So if it is 100 ml total solution in your particular conical flask, so I am going to add 1 ml each time, right, or with each step. So that is the particular case, and then I am going to say it is only going to start with step 2 because I want to see what the system is before addition of this particular component. So let us say I am going to change the concentration of what now? Let us say I am going to add base because it is H2CO3. I am going to see what is going to happen if I am adding a base. So I am looking for H plus here. Okay, it is H plus here because it is base. I am going to say it is negative, right, and let us see how we plug that in. Negative, pardon me, negative point, let us go with 1, negative 0.1, right. So what does this mean? I am going to add base, or H plus at negative 0.1 means base at 0.1 concentration to a total volume of 100 units at 1 unit each, right. So save and back to multi-sweep menu, and it is going to ask for the number of steps. So for now let us say we are going to look at 15 steps, let us say, or 20 steps. So that means a total of 20 ml is going to be added, right. And here you can have choose which particular components or compounds you want to have in your output. So, I am going to have all the concentrations of the carbonate system, right, and where else HCO3 minus. If you want to, you can look at the log concentration or activity and so on, but for now I am only looking at the concentrations of the 3 carbonate system relevant species, right. So, again 20 steps and titration manager. So, what does this mean now? So, there are going to be 100 ml, let us say I am assuming it is ml, but anyway 100 units of your volume in the flask, and I am going to add 1 unit each time, and I believe we saved that. So, I am not going to go back to here, H plus at minus 0.1 concentration, right. And let us go back to save and back and run MINTEQ, and let us see selected sweep results. So, here again I will come back to this main output menu. This is for your particular sweep 1, right, but you know that we asked the steps to be at 20 iterations, I guess, right, when we added H plus at minus 0.1 concentration. So, you can choose them individually and look at the relevant concentrations, right, or I can obviously just choose the selected sweep results, and I am going to have problem 1 to 20 and how the pH changes here and the relevant concentrations. So, obviously because I am adding a base, because H plus is negative or H total is negative. So, you see an increase in pH with each problem step, and obviously the relevant change in your particular concentrations. So, I guess here the base concentration was less, we are going to change that to be a higher concentration and look at what it is going to be, but let us look at what we have here. So, the pH is 4.1, we know that it is much less than the pKa1 of your particular carbonate system, which is 6.3. right. So, what would you expect now? You would expect that most of it would be in H2CO3, and that is what you see here, right, H2CO3, and next higher concentration would be HCO3, and the least concentration would be CO3 2 minus. Again, to refresh our memories, where is this from? We know that if you look at the speciation, let us say, so this is H2CO3 concentration, and this is going to be HCO3 minus concentration, and this is going to be CO3 2 minus concentration, and we know that the pKa1 value is 6.3, and I think pKa2 is around 10.3, and our current example has our pH at 4.1, right. So, as you see at 4.1, most of it or almost all of it is as H2CO3, and very little particular carbonate concentration is going to be in the form of HCO3 minus, and there is going to be a negligible or no amount of CO3 2 minus present at pH 4.1. Let us switch back to VMINTEQ, right, and that is what we have here 4.1, and highest concentration is of the most protonated form, which is H2CO3, and the second highest concentration is HCO3 minus, and the least will be CO3 2 minus. And obviously, as you keep increasing the pH, you are going to see a slight decrease in your H2CO3, but we have not hit pKa yet, that is the reason we have not seen a great change. So, let us go back to our VMINTEQ, I guess, right. So, I am going to change the concentration of the particular base that we are adding, and go to titration manager, and where is this here? So, I am going to change that here by saying the concentration is much higher now. Let us say it is instead of 0.1, I am going to say it is going to be 1, let us say, mole per liter, and component is going to be H plus. Let us look for that, concentration H plus minus 1 mole per liter of H plus is being added with each unit step. So, save and next. Okay, I think I did not add save and next earlier, that could be the reason why we did not see a change there. So, again let us try to do this, save and back, multi steps, 20 steps, titration manager, save and back here, and I am going to run the MINTEQ, and again look at the selected sweep results. So, that is the reason, I guess, because I did not save it earlier, we had an erroneous value. So, now we see the jump in pH from 4.1 to 8.2 with just one particular titration step. So, again I am going to move back to the particular input menu and change that again. So, I am going to delete this, I am going to have again 0.01, let us say, but it is a negative value, right, minus, again what is it of? It is of H plus, again save and next, and this is what we missed earlier, save and back, and again everything else is going to be the same. Save and back and run MINTEQ, and let us look at the sweep results. So now we have a greater variation. Now the pH is from 4.1 to 5.7, right. So again, but I want to capture the change with respect to the pKa, which is 6.3. So I am going to again increase the concentration of my particular base here. Let us see, again back to input menu and titration manager. So instead of 0.01, let me take up 10 times, I guess, right. And here the key is minus 0.1, yes. And again, what are we trying to have here? We are going to try to have H plus, save and next. So again, what does this mean? So with each unit step I am adding or with each titration step I am adding a base of 0.1 mole per liter, and obviously H total will reflect that in minus 0.1, and 100 units of the particular volume of your particular solution in your conical flask, right, and total number of steps is 20. So total of 20 ml is being added. So save and back, and hopefully now we should have the relevant results. Right, now we have the relevant results. So we have a change from 4.1 to 10.8, and we should be able to capture all these results here, right. So let us look at the change here. So 4.1, as we expect, everything will be in form of H2CO3. So 9.9 into 10 power minus 3, what does that mean? It is almost equal to 10 power minus 2. Our initial concentration of the CO3 total was 10 power minus 2, and you see H2CO3 aqueous is itself 9.9 into 10 power minus 3. But as we reach the pKa value around 6.3, right, which is at the titration step number 2, you see that the concentrations of what is it now, H2CO3 and HCO3 minus are the same, and that is what we know from our background, right. At pKa 1, the relevant protonated and deprotonated forms are going to be the same in concentration. And let us move on to 10.3, which is the second particular pKa 2, and at that particular case H2CO3 will be non-existent more or less, right, and that is what you see here, and more or less everything will be in the form of CO3 2 minus and HCO3 minus, and that is what you see here. Yes, at the pKa 2 it is 4.9 in 10 power minus 3 and 3.67 in 10 power minus 3. Let us look at the figure and see what this means. So at 4.1 everything is in the form of H2CO3, and at 6.3 we see that it is equal amounts of H2CO3 and HCO3 minus, and at around 10.3 it is going to be equal amounts of HCO3 minus and CO3 2 minus, right, and that is what we just looked at. But one issue with what we just did is that, you know, we considered that the total volume units to be 100, and at the end of our 20th step we added 20 units now. For example, to make it easier, let us assume that we have 100 ml initially, and I am adding 1 ml at each titration step. At the end of my titration, let us say I am now have a total volume of 120 ml, right. So the issue with setting up the titration step in such a way is that, you know, your particular total concentrations or concentrations are going to change because of considerable addition of your volume of your titrant, right. So where we had 100 ml, we now have 120 ml. So let us look at the way to get out of this particular scenario. So main output menu, I am going to say switch, come back to here, back to input menu. So as again, how do we do that? So go to titration manager. So we are going to say that, you know, we just want to look at the change in pH here, right. There is another way, but with respect to titration 2, what can you do? You can say that the concentration of your particular what is it now, titrant is very high, or you can show that, or you can choose that the initial volume of your particular you know, solution is very high. So instead of 100, I can have 10,000 there. You know, these are all arbitrary units, right. I can have 10,000 or so units there, and I can have a very high concentration of my particular base. Let us see what I am talking about. So instead of 100, I am going to, let us say, go up with 10,000, okay. And obviously because I am increasing that, I also need to increase the concentration of my particular acid. So I am going to say it is going to be equal to minus 1, let us say, and it is again going to be H plus, right. So again, what does this mean now? I am adding acid at higher concentrations at each step. So but because the total concentration, or not concentration, pardon me, the volume is 10,000 units, and I am only adding 20 times of 1 unit, 10,000 and 20 does not make much difference compared to 10,000, right. So this is a better way when you are trying to look at or capture the change with respect to pH when you are using the titration tab, right. Why is that again? Otherwise you are going to see to it that the concentrations of your particular components or species are going to change if your titrant volume is going to be equal to what you are titrating against. So that is one particular way. So we will not go through that again for lack of time, but there is another aspect I would like to demonstrate here, that is that we have sweep. So this is a bit more complex, but for titrations we can use that. So what is sweep about? It means one parameter is varied, right. Sweep is when one parameter is varied. So we have EH and the potential and so on, which we are not going to look at, or you can even change the total concentration of any component. So what is the additional functionality that you have here with respect to consider to titration, let us say, right. You have one parameter that is varied, but with titration, let us say earlier we had only H plus, but if I wanted to I can also have calcium, magnesium or any such parameters there or components mentioned in the titration tab. But here it is much more easier if I am just looking at the change with respect to pH, right. But again with respect to titration, it is always better if it is a complex system to look at the titration relevant chart, as in you go to titration here, right, go to titration manager. So earlier it was only H plus, so that was fine, but let us say it had calcium, where is calcium here, Ca, right, then I can only do so from this particular tab here. If I am titrating your particular my solution with against calcium, right, I have some particular solution here which I want to form a complex or precipitate, and I am titrating it with calcium, let us say. So obviously I can't use the sweep menu, I only need to use the titration menu, yes. So but obviously if I am just looking at the change in pH, I can go to the sweep menu which we are going to use and further analyze our system. So I am going to say the pH is going to change, and let us say the start value I am going to say I am going to look at the change from pH 0, and let us say the increment between values, let us say I will go with 0.5 or 0.25, let us say 0.25, and if I want to go to 14, right, and if it is 14 times 2, 28, right, 56, and I will go with 54 then, 54. So the start value and the increment between values, so obviously you need to be able to approximate. So I am trying to go to 14, hopefully 54 should satisfy my particular case here, right. So pH starts from 0, increment between each particular step is 0, 0.25, 0.5 and so on, that is what this means, and how many iterations, 54 I guess, and same case as earlier, pH, CO3 2 minus and so on, this is what I want to look at. So save and back, let me just confirm my components, they are still 0.01 and 0.02 of my H plus, right, H2CO3, and now we are going to run MINTEQ. Again you can look at the number of iterations up to 54 here, right, and the initial pH that I wanted was pH 0. Let us see what the final pH was if my calculations were right, okay, 13.25, so I should have had 3 more iterations. So anyway we will look at the selected sweep results here. So selected sweep results, and now with pH I can clearly see how the concentrations is changing. So at pH 0 obviously everything it will be in the form of H2CO3 and nothing else of CO3 2 minus or HCO3 minus, and that is what you see. So again too much data, right, in a tabular form you can never understand what is happening. So obviously I want to be able to visualize it in a better manner, so I am going to come up with a graph here. So how do I do that here? I have the option for print to Excel, okay, and thus automatically transports the relevant data to Excel, right, and let it come through. So here we have up to pH 13.25 starting from pH 0. So let us try to get the relevant graphs here, right. So I am going to look at a scatter plot for now, right, and I am going to say select data, and the chart range is going to be equal to this particular set here, yes, and I am going to have let us see if, okay, CO3 2 minus, H2CO3 and so on. So looks like I am on the right track, and so this is what I have here, right. And so what do we observe here? So please keep in mind that this is just a scatter plot, right, the actual data points were calculated here or plotted here. So the x axis is the pH 0 to 13.25 or 0 to 14 here, and y axis is the concentration. So obviously if you remember the initial concentration of H2CO3 that we put in was 0.01 molar. So, obviously the maximum concentration of any of the species can only be 0.01. And now we see with our titration how is the speciation changing. Everything is in the form of H2CO3, H2CO3 is the red here, right, H2CO3, but as we reach the pKa value around 6.3 I guess, right, we see that there is a drastic drop in H2CO3 concentration and drastic increase in HCO3 minus concentration, right. And at pKa1 which is 6.3 or thereabouts, we see that H2CO3 and HCO3 minus concentrations are equal. And as we keep increasing the pH, so if I keep moving further down at pH 8, I see that almost everything is in the form of only HCO3 minus, right, and there is no or little to no concentration of CO3 2 minus and H2CO3. And as I keep increasing the pH, what is happening now? HCO3 is decreasing, while now CO3 2 minus is increasing, right, and at pKa2 which we know is 10.3 for the carbonate system, we see that we end up with this particular graph or scenario wherein CO3 2 minus and HCO3 minus concentrations are now equal here. And as I keep increasing the pH or titrating it further such that the pH increases, what do I see here? We see that CO3 2 minus now starts predominating and there is little to no HCO3 minus present beyond pH 12 I guess, right. So, what does this tell you now? So, here if I am trying to titrate and look at the species of the various equilibrium carbonate species, what do I get? I know that there are two equivalence points. So, what does that mean now? Because H2CO3 can donate let us say 2 particular protons, right. So, here in this particular system I have 2 equivalence points, and where are they going to be? Obviously at around the pKa values, right, depending obviously on the total CO3 total present too. Again you can calculate the equivalence point depending upon the relevant formula we calculated in the last session, right. Again if it is again diprotic acid, it will have 2 particular equivalence points. Monoprotic as in let us say acetic acid, it will have 1 particular equivalence point, right. So, this is something that we demonstrate now. So, now we are going to move on to buffers, right. So, what is the point of having acids and bases now, let us say, where would you also use them practically? I guess there are many applications, but let us say I have a particular experiment and I want to maintain the pH at a particular value. Obviously I can't maintain it exactly. Let us say if I am looking for 6.5, I can't always see to it that it only changes stays at 6.5, but let us say I am okay with it being plus or minus 0.2 change. So, let us see what I am referring to here, I guess, right. Again just a particular schematic I guess here with respect to our titration. So, the pH as the base is added, right, you have the change from base here at the pKa and so on, conjugate acid is exhausted. So, this is more or less a description or a graph that is relevant to what we just discussed. So, I am going to not skip this in greater detail. So, obviously at the pKa value the relevant conjugate acid and base are going to be at the same concentration. Again as you add the acid, the pH is going to decrease and the reverse phenomena is going to be visible I guess, right. So, again I am going to move on. So, we are going to discuss buffers, and we know that in the natural systems, right, we have relevant applications and also in the engineered systems. So, natural systems we typically look at alkalinity and we will discuss this particular important aspect later on. But for now let us say we are going to consider a particular scenario where we have particular pH, or I want to maintain the pH of a system at pH 6.5, and let us say the system can produce some acid, let us say, or during the course of the experiment acid can be produced and it can bring down the pH, but I do not want my pH to go beyond let us say 6.5 plus or minus 0.5, right. I am okay with the pH staying between 6 and 7, but no further though. So, what do I do, right, or we are going to try to correlate this with what happens in the natural systems too, but let us try to understand this. So, an acid can be produced in my experiment or a base can be produced and it can affect the pH, but let us say I only want the pH to be at a particular value, because let us say I am concerned with the kinetic or effects on kinetics, let us say, right. So, how do I go about it? So, I am going to add a buffer, and what is this buffer or what is the role of this buffer, what is the objective here? I do not want the pH to change drastically, right. So, even if there is any acid or base produced, the key here is that any acid or base is produced, the buffer should be able to limit the change in pH, right. So, what does that mean now? So, it means that whenever we add or there is a change in H total, right? H total means it can it includes the addition of either an acid or a base, right? So whenever there is a change in H total, the buffer will see to it that the change in pH is relatively minimal, right? That's what my function, or that's what I expect from my buffer. Let's see what it is about, I guess. So here I have a graph, I believe. Okay, so here I have a graph, and I have pH on the y-axis, and let's say I am adding acid as I go from left to right, and I am adding a base as I am going from right to left. So obviously as I am adding an acid, what's happening to the pH here? So anyway, so this is the system here. So I assume that this is the case when the pH, when I am adding the acid, and this is the case when I am adding the base. Hypothetical example here, right? So let's say when I ask students to choose, in which regions, let's say, is the particular system well buffered, right? So please take some seconds, or few minutes, I guess, not minutes anyway, seconds, I guess, to identify those regions in this particular system when the system is well buffered. Again, keep in mind the key is that the pH needs to change less when the acid or base is added, right? So identify those regions when the pH or dpH with the addition of H plus is going to be less. So people, though, typically, I guess, because they are drawn to the intersection here, people identify this particular region as saying that it's well buffered. But let's say, I guess we mentioned this is with change in base. So here let's look at this zone. Let me erase that and come back to the ideal case. So here if I am saying that as concentration of base is added, this is the change, and let's say the hypothetical example was this is the change in pH, right? And if I am erroneous, anyway, that can be taken into account. So anyway, with base added, let's say there is not a huge lot of change in pH, right? So I am adding the base, so the pH concentration is increasing here. As I am increasing the concentration of base, the pH is increasing here, right? So and here let's say in this particular region, okay, there is less change in pH, right, when considerable base is added. Okay, that's fine. You might think that it's well buffered, but if I look at the reverse case when the acid is added and the pH is decreasing, right, and what's happening here though in the same region, let's say for the same case of the acid being added though, what's happening here? We see that in this particular region, for even a small concentration of the acid added, the change in pH is considerable, right. So what does this mean now? That it means that in this region the system is not well buffered, right. So let's try to highlight those particular aspects, I guess. So these regions, as in, if I look at these regions and this region, so even with addition of acid or base, the change in pH is relatively minimal in these particular regions, yes. So again, keep in mind that we are talking about change in pH due to addition of either the acid or the base, and not just due to either just acid or base though, right. So again, it needs to be able to resist the change in pH in both directions and not just in one direction. That is the crux of the matter. So in the next session, we are going to try to develop an equation for calculating this buffer intensity, and then maybe looking at a few applications on VMINTEQ. Okay, and I guess with that I'll end this session. Thank you.